everyone, and welcome to today's webinar, Stability of Geosynthetic Line Slopes, Part 1, brought to you by the Geosynthetics Materials Association and the Fabricated Geomembrane Institute. I'm Andy Durham, GMA Executive Council Member and Senior Geosynthetics Engineer at Owens Corning, and I will be your moderator today. GMA provides engineering support, business development opportunities, educational programming, government relations expertise, and industry recognition. GMA influences specifications and lobbies on behalf of member companies and targets key U.S. states to expand the geosynthetics market. GMA also provides a network to exchange information, solve common problems, and develop mutually beneficial relationships. FGI is dedicated to advancing the use of fabricated geomembranes through education, research, and technology transfer. Factory fabrication of geomembranes reduces field welding, reduces installation time and costs, allows modular construction, and provides consistent seam and liner quality. Please visit the FGI website at fabricatedgeomembrane.com to learn more. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You'll have the opportunity to submit text questions to today's presenter by typing your questions into the questions box of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. We'll try to get to as many questions as possible today. If we don't get to your question today, please feel free to tune into the Stability of Slopes, Geosynthetic Line Slopes Part 2, and we might be able to get to them then, or we could potentially answer them offline. The recording of this webinar and the PowerPoint will be made available after today's presentation. I'd now like to introduce our presenter, Dr. Timothy Stark, Professor of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign, with an expertise in geotechnical engineering. Dr. Stark has been conducting research on geomembranes and other geosynthetics for over 20 years. He is the Technical Director of the Fabricated Geomembrane Institute at the UIUC. Please welcome Tim.
Good morning, everyone. Thanks for joining the first of two webinars on stability of line slopes. Here are the topics for the first webinar, and the second webinar will focus on the actual stability analyses and geosynthetic interface testing to develop strength parameters for the stability analysis. So today I want to focus in on the importance, common failure modes, and the design strengths that you should be considering in the stability analysis. First, the importance of slope stability. This is a landfill, MSW landfill, and you can see some tension cracks in the soil cover that I'm pointing to. These cracks are only about maybe 1/4 of an inch, at most 1/2 inch wide, not very significant. And this is on the base near the anchor trench and going up the side slope, as you see right here. And at the crest of the slope, that's the tension crack at the crest of the slope. Again, maybe 1/2 inch, maybe 3/4 of an inch tops. And that gets to the importance of slope stability with geosynthetic line slopes. The deformations that show at the surface are generally significantly smaller than what is being experienced by the liner system and the geosynthetics underneath of it. So after some discussion, it was decided to excavate the waste in this particular site. And I'm now going to take you to the liner system. Remember, the tension cracks that you saw on the top are only about 1/2 inch, certainly less than an inch. And here's what the liner system looked like. So on the left, you can see the waste being excavated. You can see some wrinkles here in the geosynthetics on the left. Here's a close-up near the toe of the slope of the rumpled up geomembrane. In particular, the drainage composite's been pulled back. And if you were to lift up all of that crinkled and wrinkled geomembrane, there was about 10 feet of material compressed at the toe of the slope. So 10 feet, but the cracks at the top were only about 1/2 inch, certainly less than an inch. So further back, there had to be a tear, and there's the tear, or part of the tear, where the geomembrane ruptured and the slope was allowed to move and then wrinkled up and rumpled up the geosynthetics near the toe of the slope. So the failure mechanism is a translational slide, which we'll discuss in detail in a minute. I have some tension cracks, small tension cracks at the top of the slope. The failure surface goes through the waist down to the liner system or the weak material at the base, and then out through the toe. So this block moves. The geosynthetic ruptures back near where the failure surface enters the liner system, and then rumples up the geomembrane at the toe. Remember, all of that was only manifested on the slope, face of the slope or the side slope by about a half an inch to an inch. So the importance of slope stability is we have to keep the deformations of the slope very low. Otherwise, the geosynthetics will be damaged. And this is important for static and seismic design to limit deformations, both static and seismic, to small levels such that the geosynthetics are not damaged. Okay, so that's the importance of slope stability, to protect the fragile geosynthetics that are underneath. So the next segment of this webinar is 7 failure modes or common failure modes. And they are illustrated, oops, I thought I had them. They're a little later. There are going to be 7 failure modes or analysis scenarios that you should consider in your slope stability analysis. It's important to consider and analyze these failure modes to make sure they don't develop at your site. Now, that's all the bad news. The good news right now is that municipal solid waste, for example, is turning out to be a strong material. And so we really just need to focus in on the geosynthetics or the weak layers underneath of it, whether it's geosynthetic or soil. So here's a photograph of a nearly vertical scarp in MSW of about 200 feet. And that clearly shows the strength of MSW. And this photograph shows sort of the reinforced nature of MSW with the plastics, ropes, and fabrics holding it all together. So the strength of the MSW is strong, and we just need to look at failure surfaces that pass through the MSW down to the liner system. So on the right here are some typical strength envelopes for MSW. Here's a bilinear envelope that we recommended in 2009 for effective normal stresses less than 200, say a friction angle of 35 and a cohesion of 6. Greater than 200, the envelope flattens out a little bit, friction angle of 30 and a cohesion of 30 kPa as well. Now, one interesting part of slope stability that's been developing is the effect of thermal degradation on MSW and other wastes. That tends to reduce the strength, and based on some shear tests of thermally degraded waste, like the photographs at the bottom here, that those strength parameters would reduce to a friction angle of 20 and a cohesion of 0, or this red line that I'm pointing to in our MSW plot. So you can see there's a considerable reduction. So if the waste is thermally degraded, then the stability analysis should consider slip surfaces passing through the waste and staying in the waste for a longer distance than if it was just traditional MSW. Okay, 3 main failure modes: translational, rotational, and infinite slope. I gave you an example of translational in the first example with the failure surface going down to the liner system and out through the toe. So we have a strong material over a weak base. The second is rotational, and generally you'll see that with a soft soil underneath the geosynthetic line slope and the stronger material along for the ride. The infinite slope is a block on an a plane. And so if you look carefully in this photograph, that soil that I'm highlighting right here used to be up here where the road is, and it's shown over here. That's a good example of a infinite slope analysis. It's a block on a plane. There's no toe resistance. And so it's a very simple analysis of block sliding on a plane. That's also visualized by, you can just sit down on a piece of geosynthetic drainage composite and make yourself the sliding block, as you see in that photograph. Okay, here are the 7 analysis scenarios that I mentioned earlier. Liner construction, interim slope, weak geosynthetic interface, weak soil, leachate recirculation, and actually that should be liquids, and rapid waste placement and waste location. So I have a very quick example of all these 7, and then we're going to turn to the design strengths that you should use in your stability analysis. So liner construction, this is a compacted soil liner, geomembrane, cushion geotextile, and a granular drainage media above it. You can see the geomembrane's missing in this area because it slid at the interface between the compacted soil and bottom of the geomembrane. That was due to pushing the drainage material from the top down. And now you can see here drainage material is being pushed from the bottom up, and the slope is longer and remaining stable. Here are 2 examples of the same phenomena occurring. This is a bottom liner system with the cover soil being placed top down, and a cover system being top down, being pushed top down. So that should be analyzed if that's going to be the case in construction, but it's much more preferable to push the cover soil from the bottom up. Next is interim slope. This is a really important condition. It occurs a lot. Only about 5 states evaluate it. A couple states require it. All the other states really require the final condition to be analyzed, not the interim slope. And the interim slope is important because generally you have to cut the toe or excavate at the toe to attach the geosynthetics for the expansion, and then of course filling continues at the top. So this is the 2 problems for an interim slope. You excavate the toe and load the top. This is a similar interim slope on the right. The excavations at the toe, you can see a steep slope, but in addition to the excavation, there's some blasting now occurring at the toe of the slope, which has to be included in the stability analysis to assess the stability of the interim slope. Next up is the weak geosynthetic interface. This is probably the first and most looked at example of a weak geosynthetic interface. This is the Kettleman Hills case in California. First thing to notice is the valley is being filled up from the back and moving forward. And of course, this is an interim slope of about 100 feet, as we just talked about. The waste moved down the valley and toward the liner system, as you see on the right, due to sliding along weak interfaces in the double composite liner system. Here's a graph that shows the interface strengths for the geotextile geomembrane, compacted clay geomembrane, geonet geomembrane interfaces. And so this case really started looking at interface, geosynthetic interface testing and strengths very carefully. So if you look, the critical interface is the lowest strength envelope, so that's the geonet geomembrane interface, up to about 6,000 pounds per square foot. Then past 6,000 pounds per square foot, the yellow or compacted clay geomembrane interface becomes critical. So this case started showing the importance of normal stress on the interface testing, the strength of the geosynthetic interfaces, and the importance of including that in the slope stability analyses. The other important piece to notice is the interface, or the critical interface, changes at about 6,000 pounds per square foot right here. So sliding on the bottom of the landfill was on the compacted clay geomembrane interface, and along the side slopes it was between the GeoNet or geotextile geomembrane interface, as you saw in this prior photograph. Okay, here are some typical shear stress displacement curves that were used to generate some of the results that you saw. This is the peak strength that I'm pointing to, and at large displacement we get a residual or large displacement strength depending on how much deformation the shear test can undergo. The important things to notice from this graph are the strength can drop about 50% in general from the peak to the residual interface strength. So we lose about half of the strength. The peak strength, especially when there's a smooth geomembrane involved, is about a friction angle of 12 to 14 degrees. So what that means is the slope should be about 12 to 14 degrees. This highlights the importance of interface testing and the analysis of the test results, which will be a subject in the second webinar. The last important piece to get from this case history, it was substantial cost to excavate all the waste and reline the facility and reconstruct it. So very important to do the interface testing and slope stability analyses up front. Okay, next is a weak soil interface. Here's an example where municipal solid waste was grandfathered on top of an existing colluvial deposit, and the photograph that I'm pointing to on the right shows you some of the soft, saturated colluvial material that was underneath the MSW. So another example of strong material over a weak material causing a translational slide. So that's natural weak soil. And here's the failure surface going steeply through the municipal solid waste along the brown colluvial material and out through the toe. So that's natural weak soil. Here's an interesting case where the weak soil actually happened to be compacted soil. So hopefully you noticed the cover soil being placed top down. Again, not the desirable way to do it. And movement occurring in the liner system. But the important thing to notice is the geomembrane is torn, and actually the shear surface is within the compacted soil liner within the single composite liner system. Very interesting that a soil-soil interface would be weaker than the geomembrane soil interface. So when you're considering the cross-section of your liner system, you must look for the weakest interface, and it could be soil on soil instead of a geosynthetic on soil or some other material. Next up is elevated liquid pressure. So this is a MSW facility undergoing leachate recirculation. The arrow points to a couple of leachate injection wells, and you can see the liquid pressures built up, and a slide occurred into a adjacent cell that was under construction. So another interim slope failure problem, in this particular case caused by elevated liquid pressure. Once this material was removed that moved into the new cell being constructed to the right, you can see the geosynthetics are damaged, very similar to the first case that I showed you at the start of the webinar. This is elevated liquid pressures due to elevated temperatures, sort of like the thermally degraded waste I talked about earlier. Let's see if we can get this. This is a video showing you how high the liquid pressures are at shooting liquid through the interim soil cover. So those elevated liquid pressures reduce the effective stress in the slope, and that reduces the factor of safety. The picture on the right, this part of the landfill that's past the green or the grass here where the arrow is, that all moved outside of the limit of the waste because of elevated pressures within the slope. The pressure increases with elevated temperature through the gas law, or the ideal gas law. So notice that as the temperature goes up right here, R is the gas constant, N is the volume of material or moles, volume, V is the volume of material involved, and pressure is generated from this increase in temperature. So if T increases, pressure is going to increase for a constant volume and a constant amount of material and gas constant. So as the temperature increases, the pressure increases, and that causes a reduction in effective stress and stability. This can be included in slope stability analyses through a pore pressure ratio or a phreatic surface at the right location. Next is rapid waste placement. So this is a case where the facility was usually placing waste at about 5 to 6 feet per year. But the facility was going to undergo final closure, and the surface had to be regraded quickly. And so in this area where the slope failed, this area received 22 feet in the year instead of 5 to 6. That was enough to cause a failure through the native soils underneath the waste, and of course the waste came along for the ride. So rapid changes in waste placement should be considered in the slope stability analysis. Okay. Last one is waste relocation. So frequently waste has to be excavated to expand a landfill or maybe even create a new landfill cell. And when that occurs, usually the waste has a significant amount of soil in it. As you see in this photograph on the right, the shovel for scale. The unit weight of this relocated waste is about 110, 115 pounds per cubic foot. Whereas fresh MSW, as you see on the left here, maybe has a unit weight between 70 and 80 pounds per cubic foot. So your slope stability analysis should include a higher unit weight for the waste when you're using relocated waste. Also, the change in unit weight versus depth should be included in your slope stability analyses, and I'll discuss that in webinar number 2. Okay, now we're ready to look at design interface strengths. So if you're going to perform a stability analysis for one of those 7 common failure modes, and you have geosynthetics underneath the material, what strengths should you apply to the geosynthetics to perform your slope stability analysis? So 2 big issues in this segment of the webinar: stress-dependent strength envelopes and peak versus residual strengths. This is a cross-section of the Kettleman Hills case, or a depiction of it, and you can see the slope and the normal stress changes along the bottom liner system from low at the toe, maybe highest in the middle, and low again at the top of the slope. And the envelopes I showed you earlier show changes in strength with normal stress. So how do we get the peak and residual strengths? We run our direct shear or other kind of shear test to measure the peak and residual. If your shear test does not go far enough to reach the constant minimum, you should call that strength a large displacement strength and identify it with the number of inches or millimeters that the shear box or shear test underwent. Then you can plot the peak or residual / large displacement strength, and now you have two different envelopes to consider in your slope stability analysis. For many interfaces, the reduction from peak to residual is 50%, a round number, could be as high as 60%. So this is a big decision which envelope to use in your slope stability analysis, and that's what I want to discuss next. Here's how the strength loss occurs with displacement. So for your stability analyses, you can set up an intermediate or many intermediate envelopes between your peak and residual strength. So our peak strength for this textured geomembrane nonwoven geotextile interface is high. It has a friction angle of 32 degrees, good Velcro effect between the texturing and the geotextile. But as the displacements increase 50 millimeters or 2 inches, now the envelope is reduced to 21 inches. And of course, if you go all the way to residual, it's reduced to 13 inches. This is important if the analysis indicates there will be permanent deformations in the slope. So if you're looking at seismic stability and your seismic deformations are 2 inches, you have to use a friction angle of 21 degrees for that stability analysis, not 32 degrees. And of course, if you have a permanent displacement that's greater than 50 millimeters, you have to use a strength between 21 and 13 degrees. So understanding the post-peak strength loss and the deformations that you're encountering in your stability analysis is very important with geosynthetic line slopes. Okay, so design strengths. I'll start with the liner system and then look at the cover system. So for the liner system, there are two cases to consider. On the slopes involved in your two-dimensional cross-section or three-dimensional slope stability analyses, a residual interface strength should be applied. On the flat areas of the slope, you can apply peak interface strengths. So let's see how this would work for the Kettleman's Hills case that I discussed earlier. You can see there's a side slope in the back, and the bottom of the valley or cell is flat. So the slope stability analysis, if I perform a 2D analysis and cut a cross-section right through the middle here, I would apply a residual interface strength on the back or side slope, and then a peak strength along the bottom. So why does an residual interface strength have to be applied on the side slope? During construction, the geosynthetics have some creep, downslope creep. As waste is placed, that induces shear stresses within the liner system, also creating some shear displacements. As the waste settles after placement, more shear displacements occur. And so from an inverse analysis of failure of line geosynthetic slopes, we found that a residual interface should be applied on the side slopes and a peak on the flat areas. And this mainly comes from the 1994 paper that focused on the Kettleman Hills case. But there have been subsequent cases that have verified this as well as numerical analyses. So With residual on the side slope, peak on the base, you still have to meet a factor of safety of 1.5 for regulatory and slope stability purposes. Because on the side slopes, a residual interface strength will be mobilized, and thus, to have the same level of safety, you must meet 1.5. The second scenario to check is assign a residual interface strength on the slope and the flat areas. So the side slope and this base portion on your 2D section would have a residual interface strength applied to it. And there you want to make sure the factor of safety is greater than 1. So if for some reason both the side slope and peak mobilize a residual strength, you don't have a failure condition. If you use a direct shear test to measure your interface strengths, using a factor of safety of 1.1 is recommended because generally in shear box testing, you do not reach the residual value. I'll discuss next time how you can extend the results of direct shear tests on a semi-log plot and extend it out such that you can estimate the residual strength, and then you could use that for your analysis with a factor of safety greater than 1. But if you're just going to use the strength at the end of the direct shear box travel, you should use a higher factor of safety than 1.0. So that's the design strengths for the liner system. Now let's turn to the cover. The cover system doesn't induce the same level of shear displacements and mobilization of a post-peak strength that occurs in the liner system. So for the design of a cover system like the one I'm showing here on the right, you could use peak interface strengths along the slope and the geosynthetics and meet a factor of safety of 1.5. If, for example, the landfill has slopes that are steeper than your peak interface friction angle, beta is the slope angle, then you should use residual interface strengths for your cover analysis. But if the landfill is reshaped or the slope is reshaped such that the peak friction angle is greater than the slope angle, peak interface strengths can be used with a factor of safety greater than 1.5. Okay, so how do we determine our strength envelope for use in the stability analysis? Here's a 4-step procedure that I'll walk through with you using the Kettleman-Hills interface strength data. So first, we have to determine the peak and residual combined strength envelopes. To do that, we have to figure out what the critical interface is for the full range of normal stresses, determine the critical peak combined strength envelope, and then use that critical peak combined strength envelope to determine the critical residual or large displacement envelope. That's pretty confusing in a text slide, so here's a worked example. So if we go back to the Kettleman-Hills peak strength plot, at normal stresses less than 600 pounds per square foot, now it's in terms of kPa, but right about here you can see the critical interface changes from the GeoNet geomembrane to the compacted soil geomembrane interface. Okay, so my critical peak combination envelope is, that's the transition point, oops, from 0 to this point where the arrow is, and then from that point to the end of the compacted soil geomembrane interface. So that is going to be the peak strength envelope that I use in my slope stability software. I'm not going to use the full compacted clay geomembrane interface that I'm pointing to here, because at low normal stresses, that interface is too strong. the deformations will not occur on that interface. They will occur on the GeoNet geomembrane or even the geotextile geomembrane interface before they will on the compacted clay geomembrane interface. But at higher normal stresses, the weakest interface is the clay geomembrane, and so movements will occur on this interface before the GeoNet and geotextile. The GeoNet geomembrane interface strength actually increases because as the normal stress goes up, the GeoNet and the rails of the GeoNet embed into the geomembrane and give it a higher strength. Okay, so now that we have the peak or the critical peak combination strength envelope, now we can select the appropriate residual combination envelope. And that's shown on this diagram. So if you don't follow this procedure, you would use in your stability analysis the red envelope right here because that gives you the lowest strength envelope. So you would apply the red or geotextile geomembrane envelope on your side slopes for your stability analyses. But that's too conservative because the prior graph shows that at low normal stresses, it will move on the GeoNet geomembrane interface first and then the compacted soil geomembrane interface. So your residual combination strength envelope for your stability analysis would go like those two black lines that I just put on the screen. So they're from 0 to this point where the interfaces change, and then from that point to the right following the compacted clay geomembrane interface. So that residual combination strength envelope matches the peak combination strength envelope. Now, in this particular example, it's not that big of a problem because there's not a large difference between the GeoNet and geotextile interfaces or strength envelopes that I'm pointing to. But when you have a geosynthetic clay liner in your liner system, at residual strength, you essentially have the strength of hydrated bentonite, which is extremely low. And so that GCL might have a strength that's way down where my pointer is. And if you just use that strength envelope for the GCL, you'll be extremely conservative because failure might not occur within the GCL. And so you don't want to use that really low residual strength. Okay, so if I've determined my peak strength envelope, combination envelope, and my residual strength envelope, then I can set up specifications for ordering geosynthetics. So for example, this is a diagram for my peak combination strength envelope. Let's say it's this blue line right here. And notice that the envelopes are primarily stress dependent. So instead of using a friction angle, it's best to include the strength envelope in the specifications. Now, manufacturers and consultants and owners can use this diagram to figure out what geosynthetics satisfy the design requirements for static and seismic slope stability. So if a geomembrane manufacturer has a product and they want to suggest it for this particular geosynthetic line slope, they would have to run shear tests on that material, and the interfaces that are created by the geomembrane, the resulting strengths would have to plot in this green area. If they don't plot in the green area, they're not meeting the design liner strength, which is set by the blue line in the graph. And of course, if the results of the shear testing plot below the blue line, they are not high enough, and thus the geomembrane would not yield the design factors of safety that are calculated. Okay, so in summary, webinar number 1. Small displacements can damage geosynthetics. And you saw that with a case history in which the deformations were about 1/2 an inch, certainly less than an inch. And those small surface tension cracks resulted in about 10 feet or more of material being bunched up at the slope toe. So if you do see tension cracks, there's probably significant movement in or along the geosynthetic underneath. And that's because, especially in municipal solid waste, the waste is compressible, so there can be a lot of movement near the bottom, but it's not manifested at the top of the slope because it's a very compressible mass. If municipal solid waste was a rigid block, you would see 1 inch at the bottom and 1 inch at the top of the slope. So be careful when tension cracks develop. It could mean significant movement in the liner system. And of course, significant movement means damage to the geosynthetics. Second bullet point in the summary. Remember the 7 analysis/failure scenarios that should be considered. That should be a checklist. Make sure your facility, when it encounters those typical scenarios, such as liner construction, covered construction, interim slopes, check the filling diagrams between cells and evaluate the slopes between adjacent cells to make sure that an unstable condition doesn't develop. Because if the final build out of the facility is stable at, say, a 4-to-1 slope or a 3-to-1 slope, it doesn't help that the facility fails before it gets to final build out because a 2-to-1 or a 1.5-to-1 slope develops. Next bullet is the importance of geosynthetic interface testing and strengths. These interface tests should be conducted for every project. Geosynthetics differ even though they might come from the same manufacturer. So site-specific geosynthetic interface testing should be performed, and those should be performed to develop a peak combination strength envelope and a residual or large displacement strength combination envelope. Next, very important that on side slopes, any area that's inclined, that a residual interface strength be assigned. That's due to movement of the geosynthetics during placement, during filling, subsequent operation. Shear displacements will develop there because that's a weak interface, and those displacements accumulate and take you past the peak strength down to the residual strength. So with residual strengths on the side slopes, a factor of safety of 1.5 should still be maintained, and that may require flattening the slope or even a toe burn. Lastly, include liquid pressures in the analysis, especially if there's going to be leachate recirculation, and if there's a potential for elevated temperatures developing in the facility due to operation, waste accepted, hot waste, chemical reactions, or other causes of elevated temperature. That will create a liquid pressure that needs to be included in the factor of safety calculations. So the second webinar, which will be in May or June of this year, I'll focus in on geosynthetic interface testing and how to interpret those tests. Geosynthetic specifications for slope stability, I'll get into how to specifically specify the geosynthetics similar to the failure envelope I showed you just a minute ago, and then get into the finer details of conducting slope stability analyses for geosynthetic line slopes. So that's webinar number 2. Here's a list of the references that are cited on the various slides that I showed. If you would like to read more about the cases and problems that I illustrated. There's some contact information, and Andy, if we have time, I'd be happy to try to answer questions.
Yeah, thanks, Tim. Can you hear me okay?
Yep.
Okay. We do have a few questions, but definitely want to encourage the attendees to ask questions. We'll probably have another at least 10 minutes or so to do a little bit of a Q&A with Tim. So I'll start with a few questions that we have. First of all, is there a region of North America, Tim, that you see as being more prevalent than others for slope failures?
No, they're happening throughout the United States and internationally as well. So no particular area.
Yeah, are there areas that you see problematic soils or excessive moisture or any other thing that could? And what are the recipes for concern in one geographical area or versus another, or is it you have blanket issues across the board?
Yeah, I think it's blanket across the board, and the soft soil issue that can occur anywhere where you construct a landfill on a soft clay or some soft material, or in one of the examples I showed, movement occurred within the compacted soil liner. So the bottom line is gravity works 24 hours a day, 7 days a week, all across the country and the world. It will find the weak link.
Okay. Sounds good. We have another question here from Carol Sawyer. How do you determine whether a tension crack at the surface is problematic or could just be an erosion issue? I guess her question would be more of, is there a slope stability issue versus an erosion issue, and what could be some of the warning signs for that?
That's really a great question, and that's the key to your field inspection, is deciding whether that crack is a tension crack or a settlement crack or an erosion feature. So I'm going back up to the case that I was using in the beginning to illustrate a tension crack. So here it is on the screen, and notice a tension crack, literally it's like a jigsaw piece. You could push those two sides back together and they would close up that crack exactly, so it just pulled apart. Second thing about a tension crack is they will usually reappear in the same location in a short period of time. So if you cover it up, and that's not highly advisable, I'll talk about what to do with them in a minute, but if you covered it up and it's a tension crack, it'll reappear in that area in a short period of time. Whereas a settlement crack, if you cover it up, generally it won't reappear there in a short period of time because it's undergone some settlement and some other area will probably crack before that area cracks. So what should you do if you think it is a tension crack? You can put a couple pieces of wood or surveying stakes across this, put a Sharpie mark across it, and see if it's moving and measure how much it's moving instead of covering it in. If it moves in a short period of time, it indicates a tension crack. Now, that's all the good news. The bad news is, even with small tension cracks on the surface, that means there's significant movement in the liner system and probably damage to the geosynthetics in the liner system.
Okay, great. Let me see if I can follow this one a little bit from David Lutz. It's a good question. I just want to make sure I ask it correctly. Does the residual shear strength get plotted on the acceptability curve with the peak interface strength to determine an overall acceptability graph, or are these standalone and independent based on the location where the material is used? Does that make sense, Tim?
Yes, it does. That's a really great question, and I'll try to page back to that envelope. You can plot them both on the same envelope if you have a more knowledgeable group involved and they can separate the difference. I've tried that a couple times and it has led to some confusion. That's why I only plotted peak here. But you could have a second envelope where my cursor is, and you could maybe make it yellow, and that would be the residual or large displacement strength. And the knowledgeable people would know that you would compare the large displacement or residual strength to the yellow envelope, not the blue one. Most importantly is you wouldn't have manufacturers or consultants or owners comparing the peak strength to the yellow large displacement or residual strength. That's why I've separated the two. It has led to some confusion, but there's no technical reason why you couldn't include them on the same diagram.
Yeah. Okay. Paresh Desai asks, is there a cutoff for slopes that you recommend? For example, a minimum maximum slope percentage to use in peak versus residual strength?
No, there's not a firm rule like 4-to-1, 3-to-1, 2-to-1. It really depends on the interface strength. Having said that, there's at least one state now that mandates no final slope will be steeper than 4-to-1, 4 horizontal to 1 vertical, because they've experienced some slope stability failures and the state has had to sort of remediate the site. So if we don't do a better job, there may be rigid requirements or mandates of allowable slopes if we don't do a better job. But right now, they're not.
Okay. Ruben asks, Ruben says he's a drainage composite producer and concerned about friction angles. When he's given the results from laboratory tests, should he consider the peak friction angle for caps and residual friction angle for new liners?
Yep. So for cover systems, and that was this slide right here, for a cover system, if the slope is flatter than the peak friction angle, so I'll just make up a number. Let's say the geocomposite is with a textured material and you have 30 degrees. So if that's steeper than, say, a 3-to-1 slope, you can design the cover with a peak interface strength. Now, for the liner, it doesn't matter what the peak strength is. On the side slopes, the shear stresses are large enough during construction, filling, post-construction settlement, etc., that a residual large displacement strength develops on all side slopes.
Okay. Got a couple more, and then I think that'll wrap it up. Garesh asks, says that most of what was discussed here is regard to static analysis. Is there a difference in the strength of envelope for seismic and dynamic analysis and testing?
Yeah, I tried to touch on some seismic, and I'll try to do more of that in the second one. But in general, we use the static interface strength for our seismic slope stability analyses involving geosynthetic slopes. However, in the seismic analysis, the important calculation is the amount of permanent deformation induced by the seismicity or ground motion. And when that permanent deformation occurs, you must use a displacement compatible strength for the peak and residual or large displacement. So that's why this graph was so important. Here's the peak. So on the base of that landfill, let's say, it might start at 32 degrees, but if you apply the ground motion and you predict 2 inches or 50 millimeters of displacement, you have to now redo that analysis with 21 degrees instead of 32. And of course, if you use 21 instead of 32, you're going to predict a larger permanent displacement than 50 millimeters. So it's sort of a catch-22. Once the deformations start, the strengths start dropping and the deformations get even larger. So very important that you include the post-peak strength loss with displacement.
Yep, good question. So our last question, Tim, comes from Joseph Princer, and he asks, is interim slope failure common enough that it should be regularly analyzed and designed in municipal solid waste facilities, or is this kind of a hole in the regulations?
Well, at least I know 2 states that require it now, 5 that want it to be evaluated. I think it is a hole because as construction proceeds, these slopes can be steeper than the final configuration of 4-to-1 or 3-to-1. And that's because maybe there's a delay in the construction of the expansion cell, and thus waste continues to be placed, the toes excavated. So I think there's been enough problems with interim slopes that at least the design community should be considering it.
Okay. Well, great. I think that's about all the time that we have for questions, Tim. Appreciate it. Before we wrap up, I'd like to mention a couple ways to become more involved with both the Geosynthetic Materials Association, GMA, and Fabricated Geomembrane Institute, FGI. First, the GMA does Washington, D.C. lobbying twice a year. This one is next opportunity is coming up in May 16th and 17th. Would love to have you join the GMA in outreach to Congress. And also, we do several state and local lobbying efforts throughout the country in different regions. So registration is open for that, a great opportunity to get involved with the GMA and learn more about outreach and efforts that GMA does. That registration is open on the GMA website. And very important, on April 19th of this year, the Fabricated Geomembrane Institute is hosting another short course entitled Geosynthetics in Civil Engineering Applications. It's going to be in Columbus, Ohio, in conjunction with the Ohio State University. Owens Corning is also hosting a laboratory tour and reception in the evening following that short course. So details on that is on fabricatedgeomembrane.com. Again, I'll remind you that the recording of this webinar will be emailed to you if you registered later in the week, along with a copy of the PowerPoint. And I want to thank Tim Stark again. Be sure to look for details on the second part of this webinar coming up soon, and thank everyone else for attending.
Thanks, Andy.